In this video, we are going to be talking about MSC Nastran results that you get from a transient analysis. So first, we're going to look at some static displacements like you see here. We want to know what the displacement through the thickness of the cylinder is. So we're going to create this graph. After that, we're going to go ahead and look at the results of a transient analysis. So we're going to look at the change of the displacement across time at different nodes in this model. And this example is going to be problem 19, direct transient response, solids and cylindrical coordinate systems. I think traditionally we're dealing with rectangular coordinate systems, but here our displacements are going to be observed in cylindrical coordinate systems, so I'll be making a few comments about that. Now, this example is from the following document. So let me go to the cover page. This is going to be one of the Patran manuals, and here it's called Patran Reference Manual Part 6, Results Post-Processing. Again, this is going to be problem number 19 in this example. In this document, you get a description of the geometric dimensions of the cylinder, the materials, and the loading conditions. I'm going to skip all over this and just go over the results. So if you look at this document, they want a few things. Number one, they want to see the fringe plot for the deformations for the statics scenario. Then they want to look at the thickness, or rather the displacement through the thickness of the statics analysis. And then they want to look at some time histories for the displacement following the analysis of the transient analysis. Rather, they want to look at these results for nodes 120, 123, and 126. So here, let me do this. Let me go to the home page and let me close some of these windows since we are not going to be needing these windows. Now, today we are going to be using the Postprocessor web app and the HDA5 Explorer. So here I think it'd be a good time to make a few comments. Number one, the Postprocessor web app and HDA5 Explorer are free for MSC Nastran users. So if you're a student, researcher, or professional engineer, these tools are free for you to use. Also, the Postprocessor web app is only compatible with MSC Nastran. For those who are using another type of Nastran, this tool is not compatible with those other types of Nastrans. These tools are only compatible with MSC Nastran. If you want to start using these tools today, you can visit theengineeringlab.com. Here at the top right hand corner, there's a button, free download Postprocessor web app. If you click that link, fill out the form, and then we'll get you started with the installer that you can download and install the web app on your own workstation. So now here we're at the home screen of the web app. Let's go ahead and here in the bottom center, click on Tutorials and User's Guide. This is going to open the User's Guide, specifically the Tutorial section. We're going to navigate to the Postprocessor Tutorial section. If you scroll down, you'll find this table, MSC Nastran Results, CHEXA Transient Analysis and Cylindrical Coordinates. So let's go ahead and click that link. And if we look in the downloads directory, you can see that we only have a zip file that we've downloaded. Now, if we extract the contents of that zip file, I get the files that we're using today. The first file is the model, but it's configured for a statics analysis. The second file is the H5 file. This contains the statics deflections. The third file, this is going to be the same finite element model, but it's configured to perform a transient analysis. And then the last file, this is going to contain the result of the transient analysis. Now let's go ahead and do this. Let's go ahead and look at the displacement or the deflections for the statics analysis. And let me go ahead and open the statics bulk data file, and let me upload the H5 file that contains the results of this statics analysis. Here, after we upload the H5 file, the post-processor web app opens automatically. Now, when we're looking at displacement, it's very important to know what the so-called displacement coordinate systems are. Now, let me jump out of this tool and let me go into the FEM label tool here in the bottom left. Let me rotate this model a little, and then let me actually turn off the shading for the element faces. Now, this is our finite element model. Let me here on the right click on the coordinate systems. If you look in the bulk data file and you look at the nodes, you'll see that the last column here, this is going to be field 1, 2, 3, 4, 5, 6, and 7. Field 7 is actually using a different coordinate system to define the displacement coordinate systems. It's in these displacement coordinate systems where the deflections are observed for each node. Now, if we go back to the web app, here is the coordinate system 1. It's a cylindrical coordinate system. Every point here is going to have a different displacement coordinate system that's based on this cylindrical coordinate system. So here on the bottom right, if I click on this button called Display Displacement CS or coordinate system, this is going to display the displacement coordinate system for each node. These are effectively the degrees of freedom for each node. Now, if we look at it closely, look at what we have. So the red axes, this is going to be your first degree of freedom. In green is going to be your first or second degree of freedom. The blue axis here, it's going to be your third degree of freedom. So you can imagine we have translation in the red, translation in the green, and translation in the blue. We also have rotation, so rotation about the one axis, rotation about the two axes, and rotation about the three axes. Now, look at what's going on here. Depending on where you're at in the cylindrical coordinate system, depending on where you're at, this is going to determine the orientation of your displacement coordinate system. So you notice that here for this bottom node, the one direction, the first degree of freedom, is horizontal. But if we look at this other node, the first degree of freedom is actually tilted. And if you look at all these different first degree of freedoms, they're all radial. Now let's look at the second degree of freedom. So you can imagine that here, if you draw a line here, and then you swing it around this way, so imagine we're going counterclockwise, this direction is going to determine the second degree of freedom when you're dealing with cylindrical coordinate systems for the displacement coordinate system. So here, the green axis, you can imagine that it's a tangential degree of freedom. And here on this other slide, I have more details about what I mean. So let me use green. So here you can imagine that we're swinging around this way, and this is going to determine our second degree of freedom. So for this point here as an example, this is going to be the tangential direction. So this is going to be the second degree of freedom for that node. So when you're looking at the displacements are going to be one vector along this axis. So let me go ahead and erase this so it's a little bit more clear. And let me go ahead and now talk more about this. So when you look at the displacement vector in the F06 file, you're going to be given this table. You're going to be given columns T1, T2, T3, and so on and so on. Let me do this. Let me go ahead and erase this, and let me color these different colors. So T1, this is going to be the first degree of freedom. So you can imagine this is going to be the radial degree of freedom. And then what about the second degree of freedom? Let's go ahead and draw that here. So the T2 column, that's going to be the second degree of freedom. And here, let me draw a dotted line. So this dotted line is the axis of the T2 column. That's going to be along that axis. Now let's go ahead and do that for the T3. So T3 is here. This is going to be this axis with the dotted lines. So these T1, T2, and T3 I don't know how to say components rather, they're going to be in these separate displacement coordinate systems. And remember, every node has its own displacement coordinate system, and the T1, T2, and T3 components, they are in those displacement coordinate systems. I should also mention that the rotational degrees of freedom, they are also in those same displacement coordinate systems. So here, R1 is going to be rotation about the first axis. R2 is going to be in here. I know this is a typo here. So R2, that's going to be rotation about the second degree of freedom or axes. And then here, let me just correct these labels. Okay, this looks good. So again, the first rotation, that's going to be about the first axis. The second rotation, that's going to be a rotation about the second axis. And then R3, that's going to be a rotation about the third axis. And again, since the displacement coordinate system is using a cylindrical coordinate system, the orientation of each displacement coordinate system is going to be a little different. Now, what I like to do when I ever talk about coordinate systems, I like to use stick figures to help me understand what's going on. So here, for this node, you can imagine that there is a observer here. So this is an observer. And then for the next node, there's going to be another observer. And then here for this other node, there's going to be another observer. And so these observers are going to be looking at the deflections a little differently. This observer is going to report its own set of values to the F06 file. So you can imagine that's this row. So this observer is saying, hey, these are the deflections that I am observing. And then for the next observer, this observer might be saying, hey, these are the deflections as I see them. So these are what the displacement coordinate systems are. You can think of that there are different observers that are looking at the results. And then for this next observer, let's go ahead and draw an arrow here. This observer might be reporting these values for that node. So that is a brief look at the displacement coordinate systems. Here's another example. So here for this example on the left, we're using a cylindrical coordinate system to observe the displacements. So remember, there is a stick figure here observing the displacements. There's another stick figure here observing the displacements. And then here also there's another observer observing the displacements. Now, typically, if you're new to MSC Nastran, that field on the far right, field 7, it's blank. When it's blank, by default, that coordinate system is using ID 0, which is the basic coordinate system. Here on the bottom left, you could think that this is your basic coordinate system. So when this happens, you still have a different displacement coordinate system. So you can think there's a stick figure here, a stick figure here, and an observer here. So again, we still have different observers, displacement coordinate systems for each node. But the difference is that the first degree of freedom is now parallel to the x-axis of the basic coordinate system. So here, if you look at this degree of freedom, this degree of freedom, and this degree of freedom, they're all parallel to this x-axis of the basic coordinate system. So again, this is when field 7 is blank. For many of you on day 1, it's going to be blank. And here, if you look at the second degree of freedom, which is vertical in this case, this second degree of freedom for each node, it's going to be parallel to the y axis of the basic coordinate system. So keep that in mind when we're going through this exercise. We're going to be looking at the results or displacements in different coordinate systems. So, okay, let me exit out of here. And let me now go back to this post-processor web app. So again, the FEM label tool gives you an option to display what the degrees of freedom are. This tells you what the displacement coordinate systems are for each node. Now that we know this, let's go back to the post-processor web app. Here, we're going to look at the displacement. So here at the top right, let me go ahead and turn on the coloring again. Here on the top right, select the displacement data set, and then select the first checkbox for the first load case or subcase. Now here, remember, ask yourself, in what coordinate system am I observing these results? If you look at this row, you get a coordinate system option to control which coordinate system you're observing the results. Right now, we're observing the results in the basic coordinate system. So here, let's go ahead and turn on the first component of deflection. So right now, this component, here for the shape plot, I'm also going to select the first component. Now let me turn this off and on. You'll notice that in the spectrum, the deflections are very small. They're E-6, so that's a very small deflection. Let me go ahead and increase the scale factor here on the bottom right. And the reason I'm doing this is I want to exaggerate the small deflections so it's more noticeable to my eyes. So here I'm using a very large scale factor. Let me turn off the deflections and then turn them back on and off. So off, on, off, and on. You can see that here the deflection for the first component is horizontal. This is the first component of displacements that we're looking at. It's just a horizontal motion, and that's because we're observing these results in the basic coordinate system. Now look what happens when I change this to the cylindrical coordinate system. Now if I turn off the shape plot on and off, you can see that the first degree of freedom, or the first deflection, which is the first degree of freedom, it's radial. So here's the effect when we look at the results from different coordinate systems. Now here, let me do this. Let me go ahead and zoom out a little. Right now we're looking at the deflection along the first degree of freedom in the cylindrical coordinate system. And now if I scroll down a little, let me turn on the first maximum label. So this is giving me the highest deflection for the first component. And if I look here at the bottom, I'm being told that the highest deflection is happening at node or grid 22, and it's about 3.32 E-6. Now, back in the PowerPoint, if I look at this table displacement vector, if I look at the point ID column, which is the grid ID column in this case, if I look at node 22, so that would be here. So this is node 22. If I look at the first degree of freedom, if I look at that deflection, it's the same value, 3.32 E-6. So if I leave this and go back here, that's the same value we're looking at. So that's a very short overview of deflections and degrees of freedom in cylindrical coordinate systems. Now, one thing we want to do here, we want to know what the deflection or what the displacement is in the radial degree of freedom along these nodes or along the thickness of the cylinder. So what we need to do now, we need to know what the node IDs are along the thickness. So here is what the nodes are. So nodes 1, 2, 3, 4, 5, 6, and 7. Let me show you how I did this again. Let me go ahead and open the FEM label tool. Here on the right, we'll click on enter pick mode and we'll select those elements. Now, these are the 6 elements I've selected. In this checkbox, mark that checkbox, and this is going to display the node IDs or grid IDs that are associated with these elements. Here we're dealing with hexahedral elements that have 8 nodes per element, so that's why we have a lot of node IDs floating around. Let me go ahead and just look at these grid IDs. So here we have grid ID 2, grid ID 3, 4, 5, 6, and 7 along the thickness of the cylinders. So these are the node IDs we want to make a plot for. So if I go back to the home page, I'll open the HDF5 Explorer. Here I'm going to upload the H5 file that contains the results of the Nastran analysis. So here we're working with statics deflections. And then here, if I go to the acquired dataset section, here it's automatically acquired data for the 10 nodes, 1 through 10. But I want data for nodes 1, 2, 3, 4, 5, 6, and 7. So here for specify entity IDs, let me go ahead and zoom in. I've typed in those nodes, and then here I'm going to click acquire dataset. So this goes to the H5 file and gets the data for the displacements. And then here in this table, I now have the deflections for nodes 1, 2 through 7. Here in the top right, click create plot. And then wait a moment until this button here on the top middle, that starts to blink. Click on last plot added. And now I have a plot of the deflection along nodes 1, 2, 3, 4, 5, 6, and 7. So this is the deflection across the thickness of the cylinder. And if we look back at the Patran document, this is the same graph, but you can see that the graph is a little flatter than what we have here. And the reason this graph is flatter is the following. This graph, if you look at the vertical axes, it ranges between 0 and 3.6 on the vertical axes. But if I look back here, if I move the mouse cursor to the bottom until I get these arrows and I click on this bottom section, I get told that the lower bound of the vertical axis is 2.6 E-6. So it's 2.6 as opposed to 0 like it is here. So what I'm going to do here, I'm going to change the lower bound to 0 and press enter. And now you can see that the plot is flatter. And if I want to, I could do the same for the upper bound. I could make that 3.6 E-6. And here we're using the same bounds as we are as used in the Patran document. So here is the final plot of the radial deflection across the thickness of the cylinder. Now there are a few other things you could do here. You can move this plot left and right. You can move it up and down. You can zoom in if you want to. You can hide and show the plot. Alternatively, if you wanted to write out this data to CSV files so you can look at the data in Excel, here in the bottom right, there's a button called Download CSV. Here is the table of the same plot. After we download the CSV file, we can open it in Excel. And if we want to, we can go ahead and create the same plot in Excel. So here's the same plot, and then I'll leave it to you to format it a little bit more. Here, I guess right now we're looking at the magnitude. Remember, the first option is going to be the translation along the first degree of freedom. The second option is going to be the deflection across the second, the third degrees of freedom, and then we have rotations about those 3 axes. So here, let's go ahead and select the radial direction, and it's still going to be the same plot. So here, let's go ahead and modify these like we did a moment ago, 3.6 E-6. So this is the plot of the radial deflection along the thickness of the cylinder. Now there's one more plot we would like to create. Since we perform a transient analysis, we want to know what the time history is for 3 nodes, specifically nodes 120, 123, and 126. So if we look at this FEM label tool, let's go ahead and type in 120 here, 123, and 126. And let's zoom out a little. So basically, they want us to know what the radial deflection is at the inner radius and the outer radius of the cylinder. For node 123, it's actually in the middle, so they want us to know what the radial deflection is for the inside of the cylinder. But here, the post-processor web app only shows you the outer and most exterior nodes, so that's why we're not displaying node 123 here. Now, what we're going to do is we're going to upload the HDF5. We're going to open the HDF5 Explorer, and we're going to open the H5 file for the transient analysis. Now, here on the left, we're going to select the displacement dataset, and we're going to type in those node IDs or grid IDs. Grid 120, 123, and 126. We're going to click Acquire Dataset. And then here we get the data with all those deflections. So you can think that this table is going to be this table from the F06 file. So we have a T1, T2, T3, R1, R2, R3. So here we have a T1, T2, T3, R1, R2, R3. Now, after you have this data, click Create Plot. And then here at the top navigation bar, this link starts to blink. Click on this link and it'll take you to the plot that was created. Now, right now we're looking at the translation along the first degree of freedom. And you'll notice one thing about this plot. We only have data for nodes 120 and 126. What happened to the data for node 123? If we look back at the BDF file for the transient analysis, so that would be this file, you notice that the displacement command, it's pointing to 1. So if we follow this identification number, we get taken to set 1 equals 1. Or set 1. So this is going to be a pointer. Let me do this. Let me call this set 999. Here for the displacement command, I'm going to also use a pointer ID of 999. So this displacement command is saying that output the displacements for this set, and this set has the following node IDs. So output the displacements for nodes 1 through 36, node 42, and here I'm using grid and node interchangeably. So node 42, grid 43, node 49, grid 64. And if you look through the list, there is no node 123. So what I'm going to do here, I'm going to type in node 123 here on this list, and then I'm going to rerun Nastran for this transient analysis. And then we'll give it a moment to finish. Now, when I do this, and I think I've selected the wrong file, so let's go ahead and redo this again. Whenever I run Nastran, let's go ahead and open the F06 file. Let's make sure there are no fatal messages. So here there is a user fatal message. Let's go ahead and see what's going on. The keyword on the above card type is illegal or misspelled. So let's go ahead and see what happened. Let me do this. Let me go ahead and undo all these changes. Let me use the same ID 1. And now here, let me go ahead and type in 123. And let's go ahead and rerun this analysis. And we'll go ahead and open the F06 file again. Let's go ahead and look for any fatal messages now. Okay, good. So now that's been fixed. I think there might have been an issue with the identification number. For some reason, it didn't like 999. But it's okay. We fixed it. Now let's go ahead and redo this. Let's go ahead and go back to the HDF5 Explorer. So let's go through the whole process again. We're going to upload the H5 file that we reran. This time we output data for node 123. So let's go ahead and select this data set. Let's go ahead and type in the node IDs. Let's click Acquire Dataset. Let's wait. Click Create Plot. Click on Last Plot Added. Select the first degree of freedom. And now you can see that we have 3 plots. So before we only had 2 plots for nodes 120 and 126. Now we have 3 plots for nodes 120, 123, 126. Now here on the top right, there's a legend. if you look at this legend carefully, the first row of the table is telling you that the blue line, the blue curve, this is the deflection across time for node 120. So let's turn that off with the checkbox. The next row, this is going to be node 123, the transient or the deflection or displacement across time for node 123. And then here in green, this is going to be the data or the plot for node 126. So let's go ahead and turn all of these on again. Right now we're looking at the data for the first degree of freedom, and this is going to be the radial degree of freedom. Remember, these results are in the displacement coordinate systems. Here are the results for the second degree of freedom. You can see that they're a little bit chaotic. You can see that here in the vertical axes, these values are basically 10 to the negative 11. So these values are essentially 0. And look what happens when I scale this a little bit more. Let's go ahead and arrange these values between -1 and 1. So if you look at these values, up close they look chaotic. But when you scale these between -1 and 1, it's just a flat line. All of those values we saw a moment ago were effectively 0. So here, it looks chaotic, but since these are all on the order of 10 to -11, these are effectively 0 values. So there's nothing happening in these second degree of freedom. So let's go ahead and zoom out again. And let me translate this a little. So here is a flat line for those 0 values. Let's look at what's happening for the z-axis. So here again, if you look at the vertical axis, it's times 10 to -20. So again, we have 0 values here. Here, what I can do is I can scale this and move this a little bit upward. And now we're dealing with a flat line. Now, let's go back to the radial degree of freedom. This is what the deflection is. If I want to, I can zoom in. If I want to move this left and right, I can translate this. If I want to move this up and down, I can also do this. So here what I'm doing is I'm hovering the mouse cursor over the axes, and then I get these double arrows. When I get these double arrows, then I can move the graph left and right, up and down. Here in this toolbar, there's a home icon. If you click on this home icon, it'll take you back to the original view of the graph. If you want to put this image, this graph in a report, you can screenshot it. So here, let me go ahead and take a screenshot of this. So here, let me copy this. Let me go to PowerPoint and put this image on the slide. So here, you can screenshot it. Here in the top right is a blue icon that says download plot as PNG. So you can click on that icon, and then in your downloads directory, you get a new image that you can also take and dump it into a report. So here is that other image. Now, in the event you have multiple plots, let me see, I have this here. So let me do this. Let me create different plots. So maybe in this plot, we want only node 123. And then in the other plot, we want node 126. And then in this other plot, let me do this. Let me make this only the blue one. So, okay. And then for this plot, maybe I'll delete it. So we have all these plots. And let me go ahead and see what's going on here. Let me click on this button. Right, so then you can go ahead and click all these blue buttons. And you can get all these images downloaded. And you can go ahead and dump these to your final report if you wanted to. So let's go ahead and do that right now. So here are the plots that we configure, and now we have the images where you can sprinkle them in a report or PowerPoint presentation. A few other things we can do. Here in the bottom left, click on View Filters and Plotted Values. This table contains the same data in the graph. These checkboxes in this column show max peaks. This is going to label all the different peaks. So here we've marked the first checkbox. So this is the blue graph where we have the maximum peaks. Let's go ahead and turn off that checkbox. If you turn on the second checkbox, these are going to be the peaks for the orange graph, the orange plot, the orange curve. These are going to be the maximum peaks for node 123 or grid 123. And then we can do this for the last checkbox. So this is going to be the peaks for the green graph, which is going to be the transient response for node 126. So here is the same table. Here on the top right is a button, download CSV. You can download the same table, and then you can go in Excel. And then if you wanted to use Excel to make the same plot, you can do that here. And then you can go ahead and control what you want to display. Add your labels for the vertical and horizontal axes. And so, right, that is the last graph. Now, we're pretty much here at the end of this tutorial. Let me quickly recap. So number one, we went over displacement coordinate systems. We went over the deflections along the radial degree of freedom for the cylinder. And then we created a displacement versus thickness plot. So this is giving me the displacement along the thickness of this cylinder. So that would be this graph. And then at the very end, we went ahead and created some displacement versus time graphs using the HDF5 Explorer. And again, all of these tools that you saw today, the Postprocessor web app and the HDF5 Explorer, those are free as long as you're an MSC Nastran user. If you go to theengineeringlab.com, here at the top right hand corner, there's a button for you to download Postprocessor web app. Click that link, fill out the form, and then we'll go ahead and have a link to the download, or rather a link to the installer so you can download and install the web app on your own workstation. So that's pretty much it for today. As always, thank you for watching, and then I'll go ahead and stop here.